Alright, this screencast here today is going to be us going through problems that we did in class. So this will be a nice little review if you were kind of mentally focused and ready for class today, and it should be a nice little preview of what you'll see on Friday's quiz. So here goes. So we're going to do some algebra. So we need to make sure we read the problem. So a student, 58 kilograms, that's the student's mass, has a 5 kilogram backpack on. She then jumps off a stairwell of 12 meters. She then flies to the moon, where she jumps off of a 12-meter stairwell ledge. Answer the following questions. Yeah, it's kind of a funky hypothetical scenario, but it gives us something to work with and to be able to solve using some basic algebra. So we're going to be needing to reference some equations that we've used up to this point. So before we read about this equation that the distance in the y direction equals 1/2 at squared. And on Earth, we know that a is negative 10 meters per second squared. And we simplified this equation. 1/2 of 10 is 5. So we call this d of y equals 5t squared on Earth. So we'll come back and use this in a little bit, and we'll actually change this when we start talking about the moon. But for now, here goes. So we're going to be using the equation d of y equals 5t squared. We'll be using the equation velocity equals gravity times time. We'll be using the equation for weight, f of g equals mg, which is really just a derivative of Newton's second law, where f equals ma. So we're going to go into solving some problems here. So let's make sure that at any point you want to kind of review or replay what I'm solving here, go back and re-listen to it. So let's take a look at what the question's asking. It's saying, well, what is her mass on Earth and what is her mass on the moon? And we have to take in mind that she's 58 kilograms, and we're adding a 5 kilogram backpack for a total of 63 kilograms. And she's got 63 kilograms both on Earth and the moon. Mass doesn't change. Only her weight will. We'll find this out. So what is her weight in newtons on Earth? Well, here I can apply the idea. On Earth, I've got f of g, weight equals mass times gravity. So we said 63 kilograms times, right, our negative implied 10 meters per second squared, which is g. So her weight is 630 newtons. So that's on Earth. So the question here gets a little bit rowdy. So what is her weight in pounds on the moon? So I'm going to solve that down here a little bit. I want to make sure we understand that if we know that her mass is 63 kilograms, and each 1 kilogram that we should kind of get this number down, 1 kilogram weighs 2.2 pounds on Earth. I can take 63 kilograms times 2.2 pounds per kilogram, and I can get her weight in pounds, and that equals 139 pounds. So I know that if she weighs 139 pounds on Earth, where g is 10 meters per second squared, what I'm solving for, what I'm isolating here is, well, what is her weight going to be on the moon, where g is negative 1.6 meters per second squared? So I can cross multiply and divide, and I can find that she is going to weigh 22 pounds on the moon. So her weight in newtons here is 630 newtons. Her weight in pounds on the moon is 22 pounds. So question number 3, and I'll switch colors just because this is going to be pretty messy by the end of this, but stay with me. So how much time does it take her to fall to the ground on Earth? So we're solving for t. Well, if I go back to my equations, I don't know v, I do know g, so I can't use this equation here. And second law and weight, this equation doesn't even involve t. So I must be using this equation. So I am indeed using this equation. So t, how much time does it take her to fall to the ground on Earth? Well, t is going to equal the square root. We just isolated t here. So t is going to equal the square root of d of y over 5. Remember, this is on Earth. This is particular 1/2 of a on Earth. 1/2 of 10 is 5. So this is important you understand. This is on Earth. So here I have the square root of 12 meters divided by 5 gives me a time of 1.5 seconds. It would take 1.5 seconds for her to fall or jump off a stairwell of 12 meters on Earth. Oops, make sure I get this in the picture. 12 meters, 1.5 seconds. But on the moon, we got to change something. We have to change this equation here, because d of y equals 1/2 at squared. That's still correct, but it's going to be 1/2 of a, acceleration due to gravity on the moon, is 1.6 meters per second squared, times t squared. So I can simplify this just like we did 1/2 of 10. I can take 1/2 of 1.6, so it's going to be 0.8 times t squared. So now I'm still going to isolate t. So for the equations, how much time is it going to take to hit the ground? I can take the square root of d of y over 0.8. So I get 12 meters divided by 0.8, square root of the total, and I get 3.9 seconds. So the time to reach the ground on the moon is 3.9 seconds, and the time to reach the ground on Earth is 1.5 seconds. So if I were to draw then number 4, a force diagram for her in free fall in both scenarios. Well, on Earth, because I know that only f of g is going to act on it, f of g on Earth is going to be a greater magnitude than f of g on the moon, right? Because weight is going to be greater on Earth than the moon, so it's got a larger magnitude. And lastly, number 5, and I'll go back to using the black marker here for number 5. So v equals g times t. What is her velocity upon reaching the ground on Earth? Well, on Earth, v equals g times t. G is negative 10 meters per second squared, times, I have to go back and refine my time. On Earth, it took 1.5 seconds to reach the ground. So negative 10 times 1.5 seconds tells me her velocity is going to be negative 15 meters per second upon impact. And on the moon, right, so this one here was on Earth. On the moon, I know that v equals g times t, where on the moon it's negative 1.6 meters per second squared, times, I have to go back and find my time, 3.9 seconds, times 3.9 seconds, negative 1.6 times 3.9 gives me a value of negative 6.2 meters per second. So the velocity upon impact on the moon is going to be negative 6.2 meters per second. So make sure you go have a chance to check out this document on the website. It should be on the website somewhere. Off the top of my head, I can't think of where I put it. I think it was in your, I think it's labeled 1-7, but I could be wrong. Last but not least, so we're going to do these. So notice we're already doing a lot of math, and we're just putting together some more complex solving here. So I'm going to do 1, 2, and 3 here. I'll do these in red here just for the sake of just kind of moving on, switching colors. So a car is traveling down the road. You're drawing a force diagram here at a constant velocity on cruise control. So I'll go ahead and draw this and kind of label it down here. Well, if it's cruising down the road, I know that f of g is down. I know that f of normal force is up. And I know that friction's involved. So friction must be countered by the applied force of what's taking place within the car itself. So number 2, an object falling toward the Earth. So we should be getting pretty good at force diagrams. So let's do this one. Object falling toward the Earth has reached terminal velocity. I know that f of g is down. I know that f of AR is going to be equal magnitude in the opposite direction. So that is balanced, but we call this dynamic equilibrium. Number 3. So we're going to do number 3. An object is at rest on a table. So here goes. So I'm going to go ahead and start off by drawing my basics here. So here we go. So here's my object on a table. It's at rest, so I've got f of g, and the table is going to provide the support force, which is my normal force. So as I continue reading, an applied force acts on the object to the left. So here I've got a 27 Newton force acting this way, and it's got friction acting to the right, and that's only 2 newtons. So it says, what is the net force acting on the object? Well, according to this, it has a net force of negative 27 newtons, and I have to find the difference between 27 acting to the left and 2 newtons acting to the right. So this is going to be a net of 25 newtons acting to the left, which we just define here as negative 25 newtons. So the net force, this negative sign tells me that it's acting to the left. It tells me that. So this is enough, negative 25 newtons. And then 3.2 says, what is the object's motion? Well, if there's a net force, it must be accelerating. And here, I can solve for, using my equation right here, A equals F divided by M, negative 25 newtons. Its mass here, it tells me, was a 5 kilogram object. Negative 25 newtons divided by 5 kilograms tells me it's accelerating to the left at 5 meters per second squared. Remember, this could also be written as a Newton kilogram. And there you have it. Hopefully you had a chance to make sense of this. If you need to kind of slow down and go back and replay it, looking at it in parts, it might be a good idea. But there you have it. There's what we did in class today. And a lot of math.